Thank you very much for joining the web session. I'm Junpei Nozaki, CFO and Executive Business Director of ispace. On June 24th, Japan Standard Time, ispace has conducted a press conference explaining technical analysis after mission 2 landing attempt. It has been just 2 weeks and 4 days after our landing attempt on June 6th. And as you can see, we prioritize the speed to provide our information to the world. The original session, including our CEO's remarks, has been conducted in Japanese with English translations. However, we'd like to provide a direct explanation in English to a global audience what's happened to our lander on June 6th. So today, we have here our engineering team, EVP of Engineering, Hitachi-san, to explain about more details. Welcome, Hitachi-san. Thank you for joining the session. Maybe, Hitachi-san, we can start from after our landing attempt, what's happened to our lander based on your telemetry analysis. Can you explain a little more detail here?
Sure. Thank you very much, Nozaki-san. Hi, this is Yoshitsugu Hitachi, EVP of Japan Engineering Office. Now, I would like to provide a report on the technical analysis of Mission 2 landing attempt. Let us first begin by reviewing the sequence of events that occurred during the landing phase on June 6. At 3:12 a.m., this is Japan Standard Time, on June 6, the ispace conducted the deorbit insertion maneuver, marking the completion of phase 1 of the 6-step landing sequence. From there, the landing sequence progressed from left to right, as shown in this figure. Approximately 15 minutes later, at 4:04 a.m., the coasting descent phase was completed. About 10 minutes after that, the lander transitioned into the terminal approach mode upon completing the braking burn. At the time of this transition, the altitude was approximately 2.8 kilometers with a vertical descent speed of about 63 meters per second. Phase 4, the braking burn and pitch up, was completed at 4:18 a.m. However, just 8 seconds later, at 4:26 a.m., during phase 5, telemetry from the lander was lost. At the moment, the lander was at the altitude of approximately 192 meters and descending at a vertical speed of about 42 meters per second. Roughly 5 seconds after the loss of telemetry, at 4:31 a.m., we estimate that the Resilience lander had landed on the lunar surface.
Thank you, Hitachi-san. So 192 meters is the last altitude that we could confirm. And also 4:15:31 was estimated time of the hard landing of lander. Thanks for that. Yeah. Maybe you can go into more detail using the chart with about the altitude, what's happened. So next page, can we go? Okay. Can you explain this, please?
Yes. So next, I would like to walk through more details using the actual telemetry data that we received during the events. So this slide shows a comparison of the actual flight data and the simulated data used during the pre-mission planning. The vertical axis represents altitude, and the horizontal axis represents time. The blue dotted line indicates the originally simulated altitude profile, while the solid blue line shows the actual flight data. As previously mentioned, the lander successfully initiated and progressed through the landing sequence. However, at 4:39 a.m., we observed the first event, Event 1, as shown in this figure. The laser rangefinder, which was expected to begin providing valid altitude measurements by the time the lander descended to 3 kilometers, failed to do so. Then, 36 seconds later, just after descending below 1 kilometer, the laser rangefinder began its first valid measurement, marking event 2. At that time, the estimated onboard altitude was 824 meters, whereas the altitude calculated from laser rangefinder's measurement was 893 meters. So this suggests that the laser rangefinder produced a valid and accurate reading.
So again, to confirm, the important point is laser rangefinder was supposed to work at least 3 kilometers altitude. However, in reality, what's happened was the first measurement has happened at 893 meters.
Yes,
Okay.
that's correct. Yes.
Okay, thanks for that. So maybe on top of this, we can go to about the velocity.
Yes, so this is also the plot with altitude and the velocity. So before we go into the velocity, so basically you can follow this blue line. Then, as you can see, the altitude actually followed very closely the simulated trajectory until just before event 2. And then from that point on, a growing discrepancy between the actual and the simulated altitude became apparent and rapidly expanded. So this basically because of the velocity. So then now I'm going to talk about the vertical velocity here. So red line red solid line shows the actual flight data, and red dotted line shows the simulated velocity, vertical velocity in this figure. So upon receiving valid laser rangefinder measurements, the lander initiated event 3, so a full throttle rapid deceleration at 4:15:16 a.m. However, at that time deceleration began, altitude approximately 650 meters, and the vertical descent speed was 66 meters per second, whereas the simulated value was 44 meters per second. So this indicates that lander was descending significantly faster than anticipated at that point. And then 10 seconds later, at the point when the last recorded vertical velocity was 42 meters per second, telemetry was lost. So we believe that deceleration was insufficient, and as a result, the lander had landed on the lunar surface.
Okay, thanks for that. So that was what happened in terms of altitude and for velocity. Now we also have some image from NASA LRO, which indicates our landing site. So can you go to the next page, please? Can you talk about this, please?
Yes, unfortunately, so basically the hard landing, this was also confirmed by the satellite image captured by NASA on June 11th. So June 11th, following the landing attempt. On the left is an image taken on December 16th of the last year. This is before mission 2 landing attempt. In contrast, the image on the right side, so this was taken after the mission, clearly shows a new crater within this white circle. And this crater is believed to have been caused by the impact of our Resilience lander. And it is located at 60.44 latitude north and 4.6 degrees west. This is approximately 282 meters south and 236 meters east of our intended landing coordinate.
Right, so thanks to NASA, we can confirm this image, but in terms of the point, although it was a hard landing, the point was quite close to our target landing site, as you can see, like 280 meters, so on. So that's understood. Now, maybe we can move to the next point. On June 6th, we knew that the laser rangefinder measurement was not correct, but at that time, we didn't know why the issue has confirmed. Well, we couldn't identify what was the real reason for that. But maybe can you talk about what the team has done for analysis to specify the background for this one?
Yeah, thank you. So yes, this is very important. So I will explain the fault tree analysis, and which we identified the potential cause of the anomaly based on the events that occurred. So we experienced two major issues during the landing phase. Again, a delay in obtaining the valid measurements from the laser rangefinder, that's number one, and insufficient deceleration before reaching the required landing velocity, that's number two. So then, as shown in the second column from the left, so we first categorize the anomaly at this level one as potentially originating from either a software or a hardware issue. So based on the telemetry data reviewed after the event, we confirmed that no abnormalities were observed in the software responsible for the landing guidance and control. So unlike mission one, where the software was identified as a root cause, the software in the mission two functioned as designed. Then we proceeded to level two, where we examined the three possible hardware-related issues. So number one is laser rangefinder anomaly or malfunction. And second is propulsion system anomalies. And the third thing is other systems, such as power, communication, and all the other systems. So regarding the propulsion system, number two, so no abnormal behaviors was observed. So it performed as propulsion system performed as expected and following the original design parameters. Similarly, so no anomalies or no anomalies or no problems were found in the other onboard systems. So then focusing on the laser rangefinder, so number one, so we have hypothesis, so then two possible contributing factors. So number one is the error in the installation, mounting orientation during assembly, integration, or testing, or any kind of attitude anomalies during descent. And the second, performance degradation of the laser rangefinder itself during flight or the performance during the flight. And the possibility that the actual performance were below expectations from from our design. So then, for the first point, so basically we have concluded that there was no evidence of incorrect installation during the AAT or no indication of attitude control anomalies during the descent. So based on this analysis, so basically we have identified the technical root cause of the landing failure as a hardware anomaly in the laser rangefinder. So we consider it highly likely that either the laser rangefinder experienced performance degradation during flight or its actual performance was actually lower than expected.
Understood. Thank you. So we have, the team has listed up several possibilities, and as ispace, we have identified the laser rangefinder hardware anomaly is our technical reason happened for this lander failure. Maybe, so based on that, we can go further, deeper, one step more, to find out, to seek what's happened behind the scene. So.
Yeah, thank you very much. So let us now explore in more details, the potential reasons behind the laser rangefinder's performance degradation or underperformance. So as part of our investigation, we examined a range of contributing factors. At this point, we believe that four main possibilities cannot be ruled out. So first, low reflection from the lunar surface. So the first possibility concerns lower than expected reflectability of the moon's surface during the descent, which may have led to the laser rangefinder's delayed acquisition of the valid measurements. So on the lunar surface, while the landing site was known in advance to have an albedo level of 0.2, and our laser rangefinder testing was actually conducted based on this value. but we cannot exclude that possibility that the actual regolith had unexpected characteristic and resulted, resulting in lower reflectability than anticipated. And second is that, so laser rangefinder hardware-related factors. So it was known in advance that compared to mission 1, the laser rangefinder incidence angle during the descent in mission 2 was actually shallower. So the laser rangefinder's output power was also relatively lower. So these factors may have contributed to reduced reflectability and, as a consequence, delayed measurements acquisition. The number 3, it's a high descent velocity. So there is also the possibility that the lander's descent speed was too high for the laser rangefinder to obtain the valid measurements in time. As it will be shown on the next slide on more details, but our pre-flight field testing did not fully validate laser rangefinder performance under such high-speed conditions. So this limitation may have contributed to this anomaly. And number 4, so in-flight laser rangefinder degradation or failure. So although pre-launch testing, for example, radiation and thermal vacuum tests, all those tests confirmed that the hardware showed no sign of degradation under simulated space environments. We have observed however, we have observed partial performance degradation under extreme radiation levels in some tests. While such exposure levels were not expected during a typical lunar missions, however, we cannot completely rule out that possibility of in-flight degradation by the radiation.
Thank you very much, Tessan. So again, there are 4 factors, likely factors, but to be clear, at this moment, SpaceX cannot specify, select to only one factor. Rather, it could be maybe several factors might also working together, which might cause this laser rangefinder hardware anomaly. So maybe we need some more time to investigate what is final reason behind the anomaly. But you mentioned that we have another page explaining this number 3 factor, talking about the higher speed performance and the higher speed based on our field testing. So it's quite detailed, but can you also talk about this testing, please?
Yes. So yes, of course. So the as shown on this slide, so we conducted multiple tests in advance to verify the laser rangefinder's performance under various conditions. Specifically, we conducted static tests and some dynamic tests. So static tests where the sensor was kept stationary, while the manufacturer's specifications claimed a maximum range of up to 14 kilometers. But also we independently conducted outdoor field tests at locations such as Mount Takao and Tokyo Bay. And so then from there, under expected reflectability conditions, the laser rangefinder achieved a maximum range of approximately 7.5 kilometers. And also to simulate lower reflectability conditions, we also selected more like a the terrain that's more similar to the lunar environment, such as Mount Fuji and Mount Hoei. And we also confirmed a measurable range of approximately 3 to 4.5 kilometers. But the actual key challenge was dynamic testing, and where the sensor is in motion, and dynamic testing simulating descent speeds of roughly 250 to 720 kilometers per hour. So this is a corresponding speed during the descent from altitude of 3 to 10 kilometers. But in practice, it would have been extremely difficult to perform such full-scale dynamic tests over long distances, such as 10 kilometers under those conditions. But therefore, we adopted alternative methods. So at the same time, from the laser rangefinder manufacturer, we received data indicating that at speeds up to 320 kilometers per hour, the laser rangefinder could measure distances of approximately 1.5 kilometers without any noticeable performance degradation. We also conducted our own dynamic tests at Shirasato Test Center, confirming that at speeds up to 200 kilometers per hour, the laser rangefinder could accurately measure up to 1.5 kilometer without any degradation. And it's very important to note here that this 1.5 kilometer limit does not represent the maximum performance of the laser rangefinder. Instead, it reflects the maximum testable distance under the constraints of our testing environment. So another key point is while no degradation was observed at this speed, we were advised by the manufacturer that the performance degradation of up to 30% could occur at higher speeds. So taking a conservative approach, we then assumed up to 60% of degradation in the worst case, and based on the confirmed static performance of 7.6 kilometers, we estimated then that at least 3.0 kilometers of the valid range should still be achievable during high-speed descent. So with this reasoning, combining our own test results and the manufacturer's data, we believe our decision to rely on the laser rangefinder becomes operational by at least 3 kilometers was sound and well justified. We also believe this would enable a stable soft landing. However, in reality, the first valid measurement was not obtained until the lander descended to just under 1 kilometer. And we must therefore acknowledge that possibility that our assumption about the laser rangefinder's high-speed performance were actually incorrect.
Okay, thank you so much. So maybe we can go into summary about the comparison between mission 1 and mission 2. So this will be the last explanation page from your side. Yes, so can you go through the page, please?
Yeah, thank you very much. So finally, based on everything that I explained so far, so I would like to give you a summary of the key events of mission 2 by comparing them with those of mission 1. So as shown in the upper left cell of this table, the direct cause of the failure to achieve a soft landing in mission 1 was an issue with a descent control algorithm. So in other words, a software problem. After mission 1, we thoroughly identified the root cause and appropriately reflected those learnings in the redesign of mission 2 lander. As a result, as shown in the bottom right cell, so no similar issue occurred during mission 2. So we believe that the necessary improvements from mission 1 were properly and effectively implemented. On the other hand, as explained earlier, in mission 2, we identify an anomaly in the laser rangefinder, so a hardware component as the cause of hard landing. So while we currently have multiple hypotheses about underlying the factors that may have contributed to this anomaly, the further testing and specific countermeasures are then planned for the upcoming missions. So our CTO, UGA, will provide more details on the next steps.
Thank you, Hitachi-san. The most important thing about this summary is, again, mission 1 was a software issue, the mission 2 was a hardware issue, and although both involve same aspect of altitude measurement, but what's happened is quite totally different. And most importantly, we have totally revised what has happened for mission 1 software issue. So that is not the same issue happened for mission 2. So thank you very much, Hitachi-san, and thanks for your explanation. And maybe we can move to the next step by CTO Uji-san for the next action, what we are going to do for subsequent mission. So thank you very much again.
Thank you very much, Nozaki-san. Thank you.
Next, we'd like to invite our CTO, Ujie-san, to explain the next action. Hitachi-san has already explained about what are the technical cause analysis after our landing attempt. Based on that, welcome Ujie-san. We'd like to explain to the audience what we are going to do next, because we have a future missions, and it's really important to explain what is the impact and also the implication to the future missions. So again, welcome Ujie-san, and please explain about the contents, please.
Sure, yes. First of all, hello everyone. I'm Ryo Ujie, CTO of ispace. Based on the result of technical cause analysis for mission 2, as explained by Hitachi-san, now I will explain the anticipated impact on our subsequent missions and how we plan to incorporate the findings moving forward. We are currently considering 2 major improvement measures. The first is an enhancement of our verification strategy and plan for landing sensor, including the laser rangefinder. As explained earlier by Hitachi-san, we were able to confirm the performance of laser rangefinder at certain velocity and distance threshold by the field test. On the other hand, we judged high speed and long range validation was realistically difficult to achieve and hard to abandon it. Even though we are now re-evaluating our current laser rangefinder verification plan, including a challenging but variable field test with support from external experts, and seek improvement in the plan through comparison with precedent cases by an external entity. In light of the fact that we have successfully reached lunar orbit in 2 consecutive missions, yet experienced 2 consecutive landing anomalies, we take this situation very serious. To significantly enhance the performance and reliability of our landing technologies, we will not only focus on the laser rangefinder, but will also revisit the validation plans for other landing sensors. Drawing upon external expertise and lessons learned from prior missions, we aim to improve the overall sensor validation framework to ensure system-wide reliability. Additionally, we will incorporate results from the retesting of the laser rangefinder used in the mission 2 to comprehensively revise the testing strategy for the sensor in the future missions.
So, I'm sorry, so that's a corrective action number 1.
Yes,
okay.
action 1, yes.
So we can go to corrective action 2, sorry.
Oh,
yeah,
yes,
please,
yes.
please
Okay.
continue.
Yeah, sure. Yes. The second improvement is an improvement of selection, configuration, and operational use of the landing sensors, including the laser rangefinder, of course. The laser rangefinder selected for mission 2 was, based on pre-flight testing and evaluation, deemed reasonably suitable for lunar landing operation. However, it had not previously been used in a space mission. That means it was not flight proven. Moving forward, we will revise our selection criteria for landing sensor, actively incorporating external insight and placing greater emphasis on flight-proven heritage in landing sensor. For mission 3 and 4, we also plan to introduce new landing sensors, such as vision-based navigation cameras and LiDAR. Through a fundamental re-evaluation of the sensor configuration and operation, we aim to realize a more robust and reliable landing system.
Thank you. So I think there are 2 important points. Number 1 is because there was an issue of the laser rangefinder performance as a high speed. So we will revise test itself, verification plan itself. At the same time, we will consider changing the sensor itself, laser rangefinder itself. So those are the immediate two corrective actions. But maybe you also have some more, a little bit broad, comprehensive plan that our company is going to take.
Yes, sure. Yes. In addition to the improvement measures mentioned in the previous slide, yes, we also plan to implement two broader initiatives to strengthen the development of our subsequent missions. The first initiative is the establishment of an external review task force, including third-party experts. This task force will conduct an independent review of the technical cause analysis and propose countermeasures to improve ourselves. We are already in the process of selecting members, focusing on individuals with current or past experience at the major space agencies such as JAXA and NASA. The second initiative is the expansion of technical support from JAXA. Please don't misunderstand. Yes, we have received advice from third parties during past development phases, including Mission 1, Mission 2. But we now intend to strengthen this collaboration further, particularly by incorporating more active technical advice and review from JAXA. We also plan to integrate JAXA's input when translating the recommendation of the external review task force into concrete actions, leveraging JAXA's successful experience through their past lunar landing mission called SLIM. Through these comprehensive initiatives, we are committed to strengthening our development framework and significantly increasing the probability of a successful soft landing in the future missions.
Thank you so much. I think, of course, we have already done taking some external advice until today, but I think the important message is we will further enhance by having this external review task force. And also, yes, the one you mentioned about SLIM mission is very, I think, powerful, because they have done a beautiful lunar landing mission in 2024. So I think asking JAXA's support more will be a really good enhancement for ispace. So.
Yes, exactly. Yes, to improve ourselves and to go beyond ourselves, yes, we surely need to utilize external, the knowledge and experience like JAXA SLIM and so on. Then, we can surely achieve that level too, yes.
Exactly, yeah, thank you so much. This is one of the most highlighted, I think, interests from audience. What's going to be the financial impact for after this mission 2 landing attempt? And most likely we are planning to mission 3 and 4 in 2027. So can you talk about the development impact too?
Yes, of course, yes. I'm happy to mention that. Of course, the Nozaki-san is better position in the finance impact. But yes, based on the analysis result of mission 2 presented earlier, I would now like to explain the expected financial and schedule impact on the future mission. We anticipate potential impact mainly related to the reselection of sensors, such as laser rangefinder, as well as revisions and enhancement of the testing plan. From a financial standpoint, our current reasonable estimate is that the total additional development cost, including sensor selection and testing for mission 3 and 4, may amount to approximately 1.5 billion Japanese yen. However, this increase is expected to be incurred over multiple years during the development period. And then, at this time, we do not foresee an immediate need to revise our earning forecast for the current fiscal year. Regarding the development schedule, we believe the sensor reselection and updates to the testing plan can be fully absorbed within the current schedule of Mission 3 and Mission 4. Therefore, we are not currently anticipating any changes to the planned 2027 launches of these missions, Mission 3 and Mission 4. In summary, while some financial and development-related impact from Mission 2 are expected, we currently consider those impacts to be limited in scope.
Thank you so much. So I think there will be no impact in current Mission 3 and 4 schedule is a great news, I think, because it's really important for us to have to keep this mission schedule. And I think to make it clear, 1.5 billion is a maximum 1.5 billion Japanese yen, and that is both including Mission 3 and Mission 4 cost. Yes. So I think this 1.5 billion from financial perspective, of course, it's not a small. However, it's not something we cannot manage to absorb this additional cost. So I think that is also a very important information.
Yeah, of course, technically it is important to improve ourselves, but we also try to minimize the impact on the future mission too.
Okay, thank you very much. So I think those are the kind of impact towards the future missions. We have talked about the technical cause analysis, but maybe as a final of this session, maybe you can also talk about what are the achievements, because obviously we also have many achievements for this mission, from Mission 2. So can you explain about that?
Yeah, of course, yes. We didn't, reach out soft landing, but we achieved a lot of things in the Mission 2. Then, I'd like to share the key accomplishment of Mission 2. While we unfortunately did not succeed in achieving soft landing, we were still able to obtain numerous variable outcomes through this mission. I will highlight 4 of the most significant results. First one, we successfully demonstrated our reliable transportation capability to lunar orbit for the second time. Following Mission 1, we once again completed all orbital control maneuvers in the lunar orbit. It means success 8, proving the repeatability of our lunar transportation capabilities. Still, lunar transportation is a rare space mission, but we already experienced twice. We see this as a variable achievement that we will carry forward. The second one is we successfully transitioned to the descent phase while maintaining a proper landing altitude. Of course, in the Mission 1, a software issue led to a free fall from altitude about 5 kilometers, resulting in a failed soft landing. Based on that, Mission 1 lessons learned, in Mission 2 resolved that issue, software issue, and we were able to confirm the lander descended while maintaining a vertical landing posture. Now we have 2 datasets of landing sequence with different conditions, which significantly contribute to improve ourselves toward the future mission. The third one, we validated our guidance and control functionality with a final landing site deviation of less than 1 kilometer. As shown in the satellite images from lunar orbited in the Hitachi-san's presentation, the lander impacted the surface at 60.44 degrees latitude north and 4.6 degree longitude west, approximately 282 meters south and 236 meters east of the planned landing site. This confirms that the guidance and control during the final descent phase performance as expected. Lastly, we achieved significant improvement in development and operation efficiency compared to Mission 1. As we have communicated previously, Mission 2 achieved approximately 40% reduction in the development time, 50% reduction in development cost and 60% reduction in the time from launch to completion of the initial operation phase. They are the result of our effort to improve operational process through repeated missions and are key steps toward improving future mission probability and achieving overall business profitability. That concludes my presentation. Thank you.
Thank you, Ujie-san. Okay, so this concludes our presentation. Again, thank you very much for joining today's session explaining Mission 2 technical course analysis. Although, as you see, it still contains some hypotheses today. However, again, it has been only 2 weeks and 4 days after our landing attempt, and we prioritize the speed to provide the information to the world. So I really hope today's explanation helps you to understand about our Mission 2 landing attempt. And although our Mission 2 landing attempt has failed, our more than 350 global employees are committed for the future missions, and we are very much focused for the future missions. So please stay tuned, and this concludes our presentation today. Thank you very much, and have a great day.